Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we are going to talk about the t distribution. A random variable that has a t distribution is formed like this. We have in the numerator a normal, 0, 1, a standard normal that is going to be divided by the square root of a chi-square, that's represented by w, divided by its own degrees of freedom. That w has a chi-square distribution with r degrees of freedom. Okay, and as an additional condition, we have that that normal 0, 1 and w are independent. Okay. Now, what I would like to do with you in this video is deriving the probability density function for a t distribution. Okay. Now, the main idea is using the method of distribution functions that you have used before in sta360. Remember? Okay. So, let's begin. So first, remember that we said that that normal 0, 1 and that w, that chi-square distribution with r degrees of freedom, are independent. Okay? So if they are independent, the joint PDF is going to be just the product of the PDF of normal 0, 1 times the PDF of a chi-square with r degrees of freedom. Okay, so the joint PDF of z and w is, and now let me go back and take a look at our table from our textbook. Right, here we have the PDF for a normal, here we have the PDF for a chi-square with new degrees of freedom. In this case, the normal has a mean mu, a variance sigma square. So for a normal that has a mean 0 and variance 1, is just going to be 1 over the square root of 2 pi e to the negative z squared divided by 2. Right? That would be the first part of our PDF. So 1 over square root of 2 pi times e to the power negative z squared divided by 2. Right? Okay, so that's one part. Now the other part has to do with that chi-square distribution, right? This one here. So it's going to be just this guy, but instead of a nu, we are going to have r. Okay? So it's going to be 1 over gamma evaluated at r divided by 2 times 2 to the power r divided by 2. Then w to the power r divided by 2 minus 1 e to the negative w divided by 2. Okay, so here we go. 1 over gamma evaluated at r divided by 2 times 2 to the power r divided by 2, right? W to the power r divided by 2 minus 1 times e to the power negative w divided by 2, right? And that PDF applies For numbers, we know that z is going to be between negative infinity and infinity. And well, our variable w is going to be, you know, just positive between 0 and infinity. Okay, so that's our joint. Now, as I said, we are interested in finding the PDF of our t-distribution, and what we're going to be doing is using the method of distribution functions. So we are going to try and find the CDF. Okay, so that is just by definition the probability that the random variable t is less than or equal to some particular value, right? Using the definition of t, remember that t is just the ratio between a normal 0, 1 and the square root, well, divided by the square root of chi-square divided by its own degrees of freedom. Okay, so just using the definition. So it's a ratio of those two quantities. This guy here, normal 0, 1, and the square root of a chi-square divided by its own degrees of freedom. Okay, now let's rewrite that last probability using integrals. Okay, so it's going to be a double integral, but before we do that, let me just what we're going to be doing here is I'm going to be multiplying both sides of the inequality, right, by the square root of w divided by r. So I'm going to have this equivalent probability, but it's going to be easier to deal with. Okay, make sense? Okay, so here we are. Now note that z, that normal 0, 1 is going to be restricted by this, right? So in this case, what we're going to have is the integral from negative infinity to this guy here, of the joint PDF, right? So I'm going to have this guy here, and I'm going to be integrating with respect to z first and then with respect to w, and w just goes from 0 to infinity. Okay, just rewriting that probability but using integrals. Okay, now note that I'm integrating with respect to z first, right? So all the terms that do not involve z can be regarded as constants, right? So let me rewrite this. Okay, so for instance, that constant, well, we can factor out that constant. We can place it here outside our integral, right? Let me place this guy. Oh, let me copy paste this guy here, right? And then we have the w. Now I just want you to pay attention to this. Well, actually to this here, right? There. Can you see that integral, the inner integral, the one between those curly brackets? Well, that integral is the only one. It's a term that has to do with t. These guys don't have to do with t, right? And furthermore, what I want you to notice, that should remind you of something, right? That integral, the integral of 1 over the square root of 2 pi e to the negative c squared divided by 2 from negative infinity to this guy here, is just the CDF of a normal 0, 1 evaluated here. Agreed? Right? So let me rewrite it just like that. Okay, let me rewrite that like this. Oh, excuse me. Okay, so as I said, that part could be thought of as the CDF evaluated, the CDF of just a normal 0, 1 evaluated here. Okay? This part here. Okay. Now, next step. That's the CDF. So we want to obtain the PDF, right? So what we're going to be doing next to obtain the PDF is taking the derivative with respect to t. So, well, again, only this guy has to do with the term t, with the variable t. So, this is going to be the same as this. If we take the derivative with respect to t of this integral here, the derivative with respect to t of the CDF will be the PDF evaluated here times the derivative of that function, t times the square root of w divided by r, right? So applying the chain rule, what we end up with is just this, right? The derivative with respect to t of t times the square root of w divided by r is just going to be w divided by r, right? Make sense? Yeah? Are we good? Okay, so now well, now what we have to do here is do a little bit of algebra, right? First, let's evaluate a normal 0, 1 here, right? At t divided by the square root of w divided by r. Remember that the PDF of a normal 0, 1 looks something like this. 1 over the square root of 2 pi e to the negative c square divided by 2. But we're not evaluating at z square. We're evaluating at t times the square root of w divided by r. So it's going to be just t square times w divided by r, right? And then we're going to be multiplying by 1 over the square root of 2 pi, and we're going to have negative w times t square divided by r. Make sense? Yeah? Okay. So let's do that. Here, I guess I should have lowercase w, right? Anyway, I'm going to fix it now. So 1 over the square root of 2 pi, 1 over the square root of 2 pi, and then e to the power negative w times t square t squared divided by 2r. And remember that it's by 2r because we have that 2 that is dividing there. Okay? And then we could rewrite this as w to the power 1/2, and then we have the square root of r. Okay? Make sense? Okay. So what we did is we just evaluated here, right? The PDF of a normal 0, 1 at t times the square root of w divided by r. And this we just instead of writing this square root of w divided by r, I rewrote that w as w to the power 1/2 and then divided by the square root of r. Okay. Now let's try and simplify that expression. Let me tell you what's the idea behind what we're going to be doing next. Note that we have to do this integral from 0 to infinity of something that looks a little bit ugly. But if we end up with something like w to the power something minus 1 e to the negative w divided by something, that would be the kernel of a gamma, and that's the support for a gamma. So we know that if we are integrating a gamma over its entire support, the integral is 1. So that's the idea. We're going to try and make this look like a gamma. Okay? So now let's factor out let's do a little bit of algebra, and let's try and factor out no, excuse me. So, and let's try and factor out things outside that integral. Okay? So first, this guy here, we can factor it out, right? No problem. Now note something here. This is the same, square root of 2 pi is the same as the square root of 2 times the square root of pi. But the square root of 2 is 2 to the power 1/2. So let me get rid of that 2, and place it here. So I'm going to have 2 to the power r plus 1. That would be that square root of 2 that we have here. Okay? Now we have the square root of pi, we have the square root of r. Let me get rid of that guy, right? Let's place it here. We don't need this guy anymore. Okay? Now we have w to the power r divided by 2 minus 1, and we have w to the power 1/2. So let me put these two guys together, right? So that's the same. Instead of that w to the power 1/2, let me do this. Let's add a 1 here, right? And then we don't need this guy anymore. Make sense? Okay. Now note that minus w times t squared divided by 2r is the same as this, right? Minus w divided by 2 times t squared divided by r, right? So let's put these two guys together, right? So instead of e to the negative w divided by 2, what we're going to have here, right, is just a 1. So now I have this guy, right, by doing that. Make sense? So now we don't need this guy here. And let me place that term in front. This one here. Okay. Now let me factor out this guy. Okay. Make sense? Now take a look at this. This is w to some number minus 1. This is e to the negative w times something, right? So that is basically the kernel of a gamma. So let's make a little change of variables, and we're almost there. So let alpha be the following. Let alpha be this guy, r plus 1 divided by 2. Make sense? R plus 1 divided by 2. And let beta be, well, let me say 1 over beta, rather. 1 over beta be this guy. 1 over 2 times this. Okay? If that's the case, now we can rewrite our integral like this. Now we have, instead of that, we have a beautiful alpha. Now instead of this, you just have 1 over beta. Make sense? Okay? So now, next, what we're going to be doing is we're going to be multiplying by, well, dividing by the right constant and multiplying by the same constant, which is going to be just a1. So we can complete the expression for a gamma. Okay? So let's divide that by gamma evaluated at alpha and beta at alpha. Okay, but since we're dividing by that, we're going to be multiplying by that same quantity. So that's a 1. So we're not doing anything illegal. Okay, but now since we're integrating a gamma with parameters alpha and beta over its entire support, this is just a 1. Okay, times 1, right? This is just a 1. And now let's just do a little bit of algebra. Gamma at alpha. Alpha was r plus 1 divided by 2, right? So let's just substitute. This is the same as r plus 1 divided by 2, easy. Now beta to the power of alpha, that's going to be the same as the reciprocal of this guy, which would be 2 times 1 plus t squared divided by r to the power minus 1. Okay, so let me rewrite this guy, beta to the alpha is going to be the same as I said. It's going to be the reciprocal of this guy, which is going to be 2 times 1 plus t squared divided by r to the power minus 1, right? So 2 to the power minus 1, right? That's just our beta, but what we want is beta to the power alpha, okay? And alpha happens to be r plus 1 divided by 2, right? So here we go. R plus 1 divided by 2. So note that what we're going to have here is 2 to the power r plus 1 divided by 2 divided by the same quantity. Those guys are going to cancel out, right? And then so we don't need this guy anymore. And this guy here is the same as 1 plus t squared divided by r to the power minus r plus 1 divided by 2, right? Let me write that down. No. Let me just rewrite it here. Okay, so it's this guy, r plus 1 divided by 2, r plus 1 divided by 2, right? It's this guy. But that is nothing but 1 plus t squared divided by r, well, 1 over 1 plus t squared divided by r to the power r plus 1 divided by 2, right? That constant is the same, so let me place it here, and this, as I said, will be just the reciprocal, so 1 over this guy. Okay, and that would be our PDF, right? Make sense? And this holds for t's that live between negative infinity and infinity. Okay? Make sense? So what we have done here is deriving that PDF, realizing that that transformation is going to give you a t distribution. Okay, let me take this opportunity to show you what the definition of a t distribution is, but now you can see where it comes from, right? It's just the result of doing that transformation, right? And we even obtained the PDF for a t distribution. Okay, so what you have to remember is that a t distribution is a normal 0, 1 divided by the square root of a chi-square divided by its own degrees of freedom, and that normal and that chi-square are independent. Okay? Okay. And now, since we obtained the PDF, now you can see why the independence was important. That helped us to find the joint PDF. Okay? Now let me say something more about that t distribution. T distributions look similar. That would be the graph of PDF of a t distribution with 5 degrees of freedom. So as you can see, t distributions look similar to normal distributions, but they have more they have fatter tails. That's what they say. So what we mean here is that they have more probabilities. Well, they have a higher proportion of observations that are extreme. Okay? So they have more probability in the tails than a normal 0, 1 does. Okay? That's another example of another t distribution, this one with n degrees of freedom, with 10 degrees of freedom instead of 5, 30 degrees of freedom. So as you can see, as the degrees of freedom increase, then the t distribution resembles more and more a normal 0, 1. Okay? So in the near future, we're going to be using t distributions to make inferences about means, and that's why we care so much about these t distributions. Okay? Well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.